This is Pre-Algebra, Lesson 2-8. Use powers of 10 to estimate quantities. In this lesson, you will estimate large and small quantities using a power of 10. And then you also write that number as a single digit times a power of 10. For language, you will describe ways to estimate large and small quantities using a power of 10. Let's look at explain it on our first page. Keegan and Jeff did some research and found that there are approximately this many grains of sand on Earth. So many grains. Jeff says that it is about 7 times 10 to the 15th power grains of sand. Keegan says that this is about 7 times 10 to the 18th grains of sand. Who's right? Right? So that's a really big number. We have so many zeros and some digits, right? How might Jeff have determined his estimate? How might Keegan have determined his estimate? How do you think they got these numbers? What were they thinking? Let's count some zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 15. You have 15 zeros. So Jeff probably said 7 times, well, we got 15 zeros. So 10 to the 15th power, because every time we multiply 10, it seems like we're adding zeros. So if we have 15 zeros, then that's going to be 10 to the 15th power. And Keegan says 18th. Why would he have thought 18th power of 10? Maybe he's talking about digits, right? Not just zero. That's 15th digit, 16th, 17th, 18th digit, right? So who do you think is right? Who do you think has an error? Or do you think both of them are right or wrong? Right? Since Jeff counted 15 zeros in the estimated number and used the number of zeros in the original estimate, 15 as the exponent of 10. Keegan counted 18 places as he moved the decimal point to get to the right of 7. He used 18 as the exponent of 10, right? So that's part A. Whose estimate, Jeff's or Keegan's, is more logical? Who do you think? Explain it. Yes, Keegan sounds more logical because he rounded the grains of sand to the greatest place value and then counted the zeros to determine the power of 10. This is the same process that we'll use to estimate quantities in example 1. Before we do that, let's write down and record what we have talked about. Okay, again, Jeff counted 15 zeros in the estimated number and used the number of zeros in the original estimate, 15, as the exponent of 10. Keegan counted 18 places as he moved the decimal point to get to the right of 7. He used 18 as the exponent of 10. So whose is more logical? Keegan's. He rounded the grains of sand to the greatest place value and then counted the zeros to determine the power of 10, the greatest place value. So that's more logical, right? All right, let's look at focus on math practices. Do you think the two estimates are close in value? Explain your reasoning. Do you think they're both close? Like in terms of numbers? Do you think 7 times 10 to the 15 is similar or about the same size of 7 times 10 to the 18th? 10 to the 3rd power is actually 1,000. 1,000 is not a small number. No. If you divide 10 to the 18th by 10 to 15 to determine how many times is great is 10 to the 18 than 10 to the 15. you get 10 to the third. And Keegan's estimate is 1,000 times greater than Jeff's. That is not close. Let's write that down. Okay? No, it's not close. Keegan's is more accurate and closer to the actual number. You have to round the number to the greatest place value. You can't just get rid of it, right? It's going to be much smaller if you get rid of all the digits that are bigger than your zeros. All right, let's look at the next page. When would you use the power of 10 to estimate a quantity? Let's think about that as we look at our lesson today. Example 1, estimate very large quantities. Okay, what if we have a really big number? How can we use estimation to solve some problems? Janelle is comparing the estimated populations of Japan and China. The estimated population of Japan is 126,818,019. Wow, that's a big number. The estimated population of China is shown, even greater number. How can Janelle compare the two populations more easily? Okay, first you're going to estimate each population by rounding to the greatest place value. So Japan has 126,818,019 compared to the 100 million, right? 19 is very small. And also 8,000, you know, and all those other place values compared to 100 million, the other digits are less significant to affect your number, right? You're gonna just think about the greatest place value. Okay, so how many zeros do you have for Japan? 1, 2, 3, 4, 5, 6, 7, 8 zeros if you round it down to 100 million for Japan, right? Population for China, you have 1,402,941,487 population. So you're gonna round down to 1 billion. You're just gonna get rid of all the digits after the biggest the place value, right? So then you have 1 billion versus 100 million, and count how many zeros you have. That means you multiply 10 by that many times, right? So 1 billion would be equivalent to 1 times 10 to the 9th power. 100 million would be equivalent to 1 times 10 to the 8th power. Compare them. Obviously, 10 to the 9th power is greater than 10 to the 8th power. So she can use estimates using powers of 10 to compare the populations more easily. Okay, let's try this problem. Light travels 299,792,458 meters per second. Sound travels at 332 meters per second. Use the power of 10 to compare the speed of light to the speed of sound. It's really easy to see that the light travels a lot faster than the sound, just looking at those numbers, right? But how many times faster is light traveling per second, right? In order to do that, your estimation would be very helpful here. So let's estimate the light speed by 10, power of 10. So 299 million would be about, the greatest place value is 2, right? But it's 2.9, so you're going to round it up to 3. We're going to round it up as 300 million. Okay, so there are 8 zeros in the rounded number. The estimated speed of light is 3 times 10 to the 8th meters per second. Okay, what about the speed of the light? Speed of the sound, right? The second one is sound. 322 rounded to the greatest place value is 3 is your biggest digit or your first digit, right? Biggest place value, 3. Do you round up or down? Your next digit is 2. You round down, right? 2 is closer to 3. So you're going to round it down to 300. There are how many zeros? 2 zeros in the rounded number. The estimated speed of sound is 3 times 10 to the square meters per second. And comparing these two, 3 times 10 to the 8th power is a lot greater than 3 times 10 to the 2nd power. So the speed of light is a lot faster than the speed of sound. How do you figure out how many times, how much faster the speed of light is? You can divide them, right? And you can say, oh, your power quotient property says that you can subtract the powers and you subtract 8, find 2, and you get 6. So speed of light is faster than the speed of sound by 10 to the 6th power. Okay, that's another step. All right, convince me country A has a population of 1,238,000. That was a billion. 1,238,682,005. Country B has a population of 1,106,487,394. How would you compare these populations? Round them up, round them up. They are going to be both billions, right? The populations will be 1 times 10 to the 9th for both countries, aren't they? Right? When rounded to the greatest place value. So what do you do now? Then you need to round to the next place value if you see the same number when you round up to the highest place value. Okay, so you keep going to the next place value when the numbers are too close so that you can have enough information to compare them, because obviously the numbers are not going to be exactly the same. So you will compare it according to the place values, okay? Let's write that down. Okay, the populations will be 1 times 10 to the 9th for both countries when rounded to the greatest place value. So you need to round to the next place value instead. So the estimated population of country A is 12 times 10 to the 8th power now. And the estimated population of country B is 11 times 10 to the 8th power. Since they have the same power, you're going to compare 12 and 11. Which is greater? 12, right? So that's country A. The population of country A is greater than the population of country B. Okay, let's look at example 2. Estimate very small quantities. Matthias used a laser to measure the average thickness of a human hair. A sheet of paper is about 0.0013 meters thick. How do the two thicknesses compare? All right, write the estimated thickness of a human hair using a single digit and a power of 10. And then you're gonna write 0.0001777 177,632 0.0002. Why? Because if it's a really small number, then your closest place value, your biggest place value would still be the first digit, and that's 1. But you also need to look at your next digit when rounding up. Is 7 closer to 2 or 1? 2. So then you are going to round it up to 0.0002. And you will write that as a power of 10 by using negative exponents. 10 to the power of -4 means you divide 2 with 10 4 times. So that's really 2 divided by 10 to the 4th power, right? Because they're the same thing. Okay, and you're also going to write the estimated thickness of a sheet of paper using a single digit and a power of 10 using the same method. You're going to round 0.00132 to 0.001 because 3 is closer to 1 than 2. So you're going to write 0.001 as 1 times 10 to the negative 3 power and compare them. 2 times 10 to the negative 4th, 1 times 10 to the negative 3. First, you're going to look at the power. If the powers are different, then you can compare the powers. The digits don't matter. Only when the powers are the same, you're going to compare the first digits. Okay. So negative 4 is a smaller number than negative 3 in a number line, right? So 10 to the negative 4th would be dividing that number by 4 times with 10. 10 to the negative 3 is dividing it by 1,000. 10 to the negative 4 is dividing it by 10,000. So it's going to be much smaller than dividing it by 1,000. So human hair is thinner than a sheet of paper. Wow. Did you know that? Okay, look at example 3. Find how many times as much. So this is where it comes to how many times as much. I know it's bigger or I know it's smaller, but how many times as much is this bigger or is this smaller, right? So how does the gross domestic product, GDP, of Canada compare to that of the United States from the information given? We have a really big number because it's a GDP for the whole country. GDP for Canada is, what is this? We got how many zeros? 1,000, million, billion, and that's trillion. We got quadrillion, okay? USA also has 17 quadrillion, right? 15 zeros, wait, 15 zeros until 1, right? So that's going to be quadrillion. Wow, okay. But step 1, you're gonna write each GDP as a single digit times a power of 10. This is also called the scientific notation. You have a single digit times a power of 10. Okay, so Canada, you will round 1.7 as 2 because it's closer to 2. 2 times 10 to the 15th power is about the estimate of Canada's GDP. USA's GDP is about 2 times 10 to the 16th power. Okay, so we're really talking about 2 quadrillion versus 20 quadrillion. Obviously, which one is bigger? 20 quadrillion, right? 10 to the 16th power is greater than 10 to the 15th power, right? So you are going to say USA is greater, but by how much? Your digit 2 is the same. So what do you think? You divide the bigger number by the smaller number to see how much bigger the bigger number is. So 10 to the 16 divided by 10 to the 15, using the quotient property of exponents, you subtract the powers and you get 10 to the first power, which means the US GDP is about 10 times greater than that of Canada. Okay. So examples 1 and 2, you can just compare them. This is greater than or this is less than. Okay. Example 3 is about finding how much times greater exactly or smaller exactly, right? Let's try this question on the bottom. There are approximately 20 million cars in the world. The number of cars in the United States is approximately 239,800,000. Compare the number of cars in the world to that in the United States. You already know that the number of cars in the world are going to be greater than United States. But compare how much is it greater than United States? Or how much smaller is United States compared to the numbers of cars in the world, right? So think about it, solve it, and come back when you are ready. All right. You can estimate the number of cars being about 1 times 10 to the 9th power, and United States to be about 2 times 10 to the 8th power. Okay? Count the place values before the first digit. And how much greater is it? You put the bigger number first on top of the fraction. Smaller number, you divide it. And so you have 1/2 times 10 to the 9 minus 8th power. Okay? Which is 10 divided by 2. What does that mean? It's 5 times greater. Okay? So you can say there are about 5 times as many cars in the world than in the United States. But guys, this is really big. Like United States have a lot of cars. This does mean that United States do have a lot of cars because we have a lot of countries in the world. And if you total the number of cars in the world, and that's only 5 times as many cars in the world than in the United States, that means United States overrun like so many other countries combined in the number of cars, right? Yeah, so if you ever lived in the United States, you really need car, unless you're living in a big city. All right, let's look at the key concept to summarize our lesson. What did we learn today? You can estimate a very large or small number by rounding the number to its greatest place value and then writing that number as a single digit times the power of 10. We learned how to estimate big numbers and really, really small numbers. Okay. So you should have understood how to write very large and very small quantities using powers of 10 and use those numbers to make estimates. All right, that was 2-8, use powers of 10 to estimate quantities. I will see you in the next lesson. Bye.